Hi there, this is Dr. John, your physics and math professor, and today we have another problem that deals with blocks and friction and forces and all those sorts of things. So hopefully this very simple problem will help you to solve some of the more difficult problems as you go along. So here we have a block sitting on a table, and the table has a coefficient of friction between the table and the block of 0.65. And the block weighs 3.75 kilograms, and a force of 45 newtons is being applied to the block. We're supposed to find two things. First of all, the force of friction, and then find the acceleration of the block. Now, just to give you a little bit of a background, first of all, just so you understand what we're doing here, is that we're dealing with Newton's three laws. You don't need to memorize Newton's three laws, but have a general idea of what they mean. So the first law is sort of the law of inertia. If something is sitting still or something is moving at a constant velocity, it's going to continue to move unless acted upon by an unbalanced force. So in other words, if the forces to the right are the same as the forces to the left, then it's going to continue to move on. But if there's more force in one direction than the other, then it's going to accelerate in that direction. Well, that's what the second law says. The second law says that the mass times the acceleration is going to be equal to the force. So if something is going to have a net force or an unbalanced force or a sum of all forces, then that's going to equal the mass times the acceleration. The higher the mass, the less the acceleration. Again, these things seem sort of straightforward and common sense to us, but in Newton's time, they were quite dramatic and revolutionary. And then the third one is just simply for every action, there's an equal and opposite reaction. If you push on a wall, it's going to push back on you. We're going to use those laws for all of these kinds of problems that we do. And so what we want to do, first of all, we want to look at this block and examine the different forces acting upon it. So what I've done here is I've sort of sketched out a multicolored drawing. Here's the box in the center. This going downward is the force of gravity, the green one. That's just mg, pretty straightforward. And then there's the normal force going upward. So normal just means perpendicular. So let's say you have a surface like this, and you have something drawn at 90 degrees to that. This is called a normal. So a normal force is a force that acts exactly at 90 degrees or perpendicular to the surface. In this case, notice that since this doesn't buckle down or buckle up, that means the up and down force, the normal force, has to be equal to this, which means we can actually put a little equal sign in there. This is going to be equal to this, which is mg. So now we already know what the normal force is. Now we're dealing with the left and right forces. Left and right is where we're going to get some acceleration. We have a force of friction, and we have the applied force in blue here of 45 newtons. And we want to know the acceleration. Remember what Newton said in his second law is that if there's a net force, an unbalanced force, that's going to cause acceleration. So we have the applied force and we have the force of friction. Now the force of friction will never be bigger than the applied force. It may be equal to the applied force. There's two different kinds of coefficients of friction. Here's a coefficient of friction. Sometimes they'll put a little subletter on it, mu s. This little mu s stands for static. And this little mu k stands for kinetic. I know, again, those are strange words to use and they may seem a little bit unusual. Static just simply means it's not moving. Static cling, things that are static, they're not moving, they're not changing. So this would mean if you have a coefficient of friction and that friction, like Velcro, is holding the block to the table really strongly and you're pushing, but you're not pushing with enough force to overcome the friction to loose the Velcro, to pull it off, then you're going to have something called static friction. In that case, the friction will continue to increase and be equal to the force. Until you rip it loose, then the friction will be less than the force because you're actually going to accelerate it. Kinetic coefficient of friction is that coefficient of friction when you're already moving. Because when you're moving, things don't have a chance to tie down. It's like the bonds don't have a chance to form. And you don't have time to form friendships between the table and the block. The important thing about this is that the static friction is always a little bit higher, which is one of the reasons why when you go around a curve in a road, you don't want your tires to slip. You want them always to be touching the road. You want it to be static friction because this is better. It holds onto the road better. But in this case here, we're dealing with kinetic friction. We don't actually have a subletter on it. I just shared this with you so that you would understand that as a basic foundation. We're going to be using that later on in our course. So we're going to be dealing here with kinetic friction. I could put a little K beside there, but I don't have to. I can just leave that blank if I want to. It's just the coefficient of friction in this case because the block is going to accelerate. The coefficient of friction, by the way, is between 0 and 1 in practically all cases. For something like ice or something very smooth, it might be 0.1. For something like concrete or gravel, it might be 0.8 or 0.9. It might be quite close to 1. So this is actually a fairly high coefficient of friction. We want to find the force of friction. Now you may have remembered this formula from before. The force of friction is going to be equal to the normal force times mu. Now notice that the normal force N is in newtons. It's already a force. And the force of friction is also in newtons. It's also a force, which means that mu, the coefficient of friction, has no units. It's just a number like 1 or 0.5 or something. It has no, you don't put meters per second, you don't put newtons behind it. It's just simply a number. So that's why there's no units behind this. There's units behind this and units behind this, because you're already multiplying one force to get another force. So if this had units, it would change this from being a force to being something else. Since we know that the surface is not buckling up and down and the normal force is equal to mg right here, and we know what the coefficient of friction is, we can calculate the force of friction, which is just simply going to be equal to mg times mu. Plug the numbers in there. M is 3.75, g is 9.8, and mu is 0.65. I like to have my students do a quick estimate to sort of before they plug things into their calculator, and just do it really roughly. So this is close to 5, this is close to 10, so that's about 50, and this is close to 1/2, so it's going to be about 25. Of course, I'm making really rough estimates. Let me do my calculator and see what I get. I'm actually getting 23.89. I'm getting that the force of friction is equal to 23.89. I actually did this rough estimate in my head. I didn't actually know what the answer was before I checked. So that's amazingly close for a guess. This kind of guessing allows you, if you're making stupid mistakes in your calculator, it'll keep you from doing that. So since one of the answers they wanted here was the force of friction, we'll always want to check significant figures at the end. Before you get right to the end, you can keep an extra digit or two. Don't keep like 10 digits. But notice here there's 3, 2, and 2. So we'll want to keep 2 significant figures at the end. Since this is 23.89, that would be, the answer would be 24. So the answer over here is force of friction equals 24 newtons. Pretty straightforward. Now we've got 2 significant figures. We can keep using this though as we do the acceleration. Don't, when you do your rounding, make sure you write that only for your final answer. So let's keep using this as we find our acceleration. Let me erase a couple of things here. Okay, now that we have this, let's do the last step, which is we want to find the acceleration of the box. To find the acceleration, remember we said that the net forces is what matters. Well, we have a force that we're pushing this with, and we have a force that's pushing back or resisting motion like this. So we're going to have to take 45, which is the pushing force, minus 23.89. I'm getting 21.11. Again, obviously I'm keeping too many significant figures, but we'll drop some in a second. So that's going to be our net force. That's taking all the different, and we're just going left and right, because up and down we've already balanced it. So this is the net force to the right. That's going to cause acceleration. Remember Newton's law? Force equals mass times acceleration. We want to find the acceleration, which means we have to divide both sides by mass, which means acceleration equals, take this under here, the force divided by the mass. So the net force, that's what we're looking at here, which is 21.11, divided by the mass, 3.75. This is going to give us our acceleration of the system, which looks like, ignore all these numbers, it's about 7. I am getting the acceleration equals 5.6. It's a little bit less than 7 here because I forgot this is closer to 4 than it is to 3. So let me erase a couple of things and then we'll just double check our significant figures here. So 5.6, 2 significant figures, 2 significant, this is 3, so we can leave this like this. 5.6 meters per second squared. There we found the force of friction that opposes the motion. We found the acceleration. We're finished with this problem. Like I said, it's a very simple one, but I went into a couple of other things that might help you to understand and do harder problems. If you like this video, like it and subscribe to my YouTube channel, and I'll see you in the next video. Bye-bye.